Chapter 3, the derivative of a function. So far we have done is the derivative of a point, which is at a. Now what happens if we want to take the derivative of the function as a whole? Well, we just simply replace a with x. To be exact, the definition of the derivative on page 232 of your book says that let f be a function, then the derivative, which is denoted by f prime of x, the derivative of a function at any point x, is given by a very similar looking definition as before, which is this familiar thing. We'll define it with the h notation. That is, h goes to 0, where you have f of x plus h minus f of x, and then all divided by h. And that is the definition of derivative in general. And of course, we have a basic condition that this limit better exists. Okay, a function is called differentiable if this particular limit exists. If it doesn't exist, then it is not differentiable. And a function that is differentiable on a certain domain is called a differentiable function for the domain. Now, first, let's skip over to the next page. We'll come back after that. Let's skip past example 3.11. Go to the next page, and I want to talk briefly about the notation business. Let's briefly look at page 234, where we talk about the notation. Page 234, we talk about the notation of the differentiable function is called f prime of x, or the derivative function is called f prime of x. But there's more than one way to express it. There is also, as in your book, top of the page, f prime of x is sometimes also written as dy by dx. This is the exact same thing as this. Okay, this is not a fraction, even though it looks like it. It's just this thing. The y represents f of x. Okay, where y equals to f of x. And for that reason, this thing can also be written like this: d f of x by dx, which again, it just means this, which is this, right? F prime of x, which is the derivative function, is also called dy by dx, which is also called d of f of x by dx. Remember, this is not a fraction at this point. It's just a way of doing it. In fact, f prime of x can even be written down as y prime. That is, y prime equals to f prime of x, and y prime, which represent the derivative function. Yeah, I think that's about all the notations. Oh, one more thing. The derivative at a certain point, that is f prime of a, f prime of a, which is the derivative at the point a, can also be written like this: dy by dx at a. See this long straight line down there? Means the derivative is being evaluated at a. So now knowing all this, you're thinking, why are there so many different notations for the same thing? Well, it's tradition. As a mathematician, as a math student, you should respect the tradition. So, okay, now that we said that, let's go back to doing some example. We'll go back to page 232 where we were before. And I just want to mention the notations real quick. Okay, now let's try to do something. Let's try to get a derivative function out of something. Okay, example 3.11. This is still on page 232, where we find the derivative of a simple function, square root of x. So your f of x equal to square root of x, and we want to find what is the derivative of this thing. To find the derivative, we will follow this formula, right? This neat little formula. Yeah, and then do this. So following the formula, we'll write down all the stuff. F prime of x, by definition of this thing, is the limit as h goes to 0 of f of x plus h is square root of x plus h, and then minus f of x, right, which is the square root of x, and then divided by something, just h. All right, then we have to evaluate this limit. I think I'll write this way, it might be easier. So, okay, now to do this calculation, we have to go back to that same trick that we use every day, it seems. That is the difference of squares. A squared minus b squared equals to what? The plus and minus. Okay, a plus b times a minus b. And why are we doing this? We are doing this in this case for the purpose of getting rid of the sum of the radicals. Because as of right now, how will we calculate this? This is h is going to 0, and we need to figure out some way to cancel it out, okay? Because we cannot divide by 0. And so we'll do this by multiplying. See, this is a minus, and we'll pretend that this is the a, and this is the b in my difference of squares formula, and then multiply by the plus version. See, we'll have the minus one, we'll multiply it by the plus one, and that'll get rid of some of the square roots. So pulling that trick, this equal to limit, you write this down again, x plus h minus square root x and over h, and multiply by something that's the same top and bottom, so that it equals to 1. This thing equals to 1 because the fraction has the same value here. So when you multiply something by 1, you don't change its value. So we'll multiply specifically by the plus version. And we'll do the same thing top and bottom. X plus h, so you write it again, square root of x. All right, now once you get the difference of squares, then you have very neatly just the thing itself, right? So you have x plus h minus x left on top. Okay, and then on the bottom, then you have h times this pile of stuff, which is h square root of x plus h plus, well, we'll just write it like this, I guess. Square root of x. All right, we don't have to multiply it out for a specific reason. You notice that x minus x, it disappeared, because at this point we're considering where h is very small but not 0. Therefore, there's only h left on top, and therefore you can cancel it out. See? Because h is not 0. H is simply very small. So at this point, we can calculate continuing calculation. H is going to 0. Of when this is canceled out, then you have 1 left. Okay, not 0, 1, because you are canceling. And in cancellation, you are left with 1. And then and the bottom you have left very neatly x plus h plus square root of x. And check this, h is going to 0, but now the denominator is not going to 0 anymore. And so that equals to 1 over h disappears, so you just have 2 of the square root of x left. So it's quite neat. You have a nice, neat, clean answer. And that is what we were looking for, is the derivative of f of x. If f of x is the square root of x, then f prime of x is equal to this thing. And that is the answer. Now for the next example, example 3.12, I ask you to do that at home yourself. It's slightly easier than this one, but it's more tedious. It takes, you do a lot of algebra, as in addition and subtraction, that kind of thing, and try not to make a mistake. So, but once you go through that, you should be able to do example 3.12 without a problem right here. The way you do it is you write down the problem and then you cover the answer and then do it yourself. And if you have any trouble, then look at the answer and see what the book explains. So that's that. And I should mention now, next page, I forgot to mention something over here. All these different notations. There's something else that I should mention is there's such a thing that this particular notation here is also written as the triangle y over triangle x. Okay, now it is another definition for the derivative. I'm talking about this part. In other words, the triangle is pronounced as delta. So in other words, the dy by dx here can also be written as the limit of delta x goes to 0 of delta y over delta x. The triangle is pronounced as delta and is another Greek letter. The delta y is one variable. Okay, so that's why it says delta x goes to 0. Sorry, delta x. This says the same thing. This all says the same thing. Is delta x is the amount changed in x, and delta y is the amount that got changed in the y value. But I just want to explain that this is the triangle is pronounced delta, like the airline. So the delta, this is pronounced as delta y over delta x, and the derivative can also be defined as limit of delta x goes to 0. So if you see it, don't be puzzled. That's what this means. And that's yet one more definition of the derivative, or one more notation way of saying it. And like I said, it's tradition. Okay, it's tradition to be able to know all the stuff means the same thing, the derivative. All right, now I'll clean the board. Now when you finish example 3.12, you will notice that while your function f is some kind of parabola, the one down here, I am at page, what page is that? 235. So anyway, so while your function might be some kind of a parabola, the derivative is some line. See, it goes like this, and that is because the derivative only calculates the slope of the function at every given point, and so it end up looking very, very different. Now to check that, let's look at example 3.13, where you look at a function and you guess what as a graph, and then guess what the derivative look like. It's actually not a guess. You estimate. Okay, you look at the function and then you estimate what the derivative might look like. So here's how you do this. It's very important to bear in mind that there are very different things. A function almost never looks like its own derivative, unless it's 0 or something. Then everything is 0. So, but yeah, well, so let's look at some random function. This is example 3.13, and we are on page, let me write this stuff down, page 335. What? 235. 235. And we're looking at example 3.13. All right, so look at the graph. Oh, sorry. So let's say we have some random graph that looks randomly like this. Okay, here's your graph, and the graph looks, it goes down here and then goes up here, something like that. All right, here's your random graph in the book. Now, what does the derivative look like if we were to estimate it, to have an idea? The way you know is when you think about derivative, you're thinking about the slope only. So at first you notice that this part is flat. Okay, anytime it's flat, the slope is 0. Remember that. The derivative is the same as the slope of the graph. So at this point, your derivative graph has to be 0. So we'll draw it down here. The same as here. See, at this point, the graph is flattened. When I say flat, I mean level. The graph is level again, right? So therefore, at this point, this thing is also 0. And then at this point, the value is the graph is sloping down this way. And if stuff slope down this way is a negative, okay? When it slope this way is positive. So this value around here is somewhere negative, whereas this thing is somewhere positive. We don't know how much. Well, we can sort of tell by how much is going up. If it's really steep, then it's very positive. If it's not that steep, it's whatever. So, but for now, we'll just draw it as some positive line, and then this is negative again. So it's down here again. So the derivative slope in our estimate is something like this. It goes up and become positive, and then crosses. It becomes 0 again, and then become negative again. Something like that. So that's our rough estimate. It's an estimate, but it's not exactly a guess. We do know that this point is 0, so that's for sure. We don't know how positive it got. I mean, not unless we calculate this exactly. But we know it's positive, and then we know that it hits 0 again, so it got down again. That sort of thing. So that's how you estimate something like that, which is a quick estimation. All right, now moving on. Next, theorem 3.1. If a function is differentiable, then it is continuous. There's a reason for that. Is because the definition of differentiation, it includes within it a continuity. Now, to be exact, let's look at this. Okay, we'll go through the proof of the differentiation implies continuity proof, because it's a straightforward, neat little proof, and it's worth us looking at it. So theorem 3.1. Differentiation implies continuity. Now, if something's differentiable, it is of essence, it is necessarily continuous. Now, how do we prove that? So here what we're trying to prove is if f is differentiable, then f prime exists. See? So here's what we're trying to prove, which is what the theorem says, is differentiable, okay, implies continuous. This is always. Okay. Now, how do we prove that? So to prove that, we have to show that something. Show the definition of continuity. That is, here's what we're given, right? Differentiable at a certain point, let's say A, means this particular relationship exists. Equation exists. F prime of A equals to limit x approach A, f of x minus f of A over x minus A. Now this is different from our original definition, because our original definition used the h kind of formula, but from previous section we know that that's the same as this one. Okay, those two are just slightly different ways of saying the same thing. So we'll use this formula in this example because this is somewhat simpler than using the h one. So therefore, so this is what we are given. Okay, the function is differentiable at A. How do we get to continuous? Well, first we got to know what is continuous. Continuous means here's a definition of continuity. The definition of continuity says that the limit, it just means that the limit as x approach A of the function of f of x equals to A, equals to f of A. That's the definition of the limit. So that when things get close, it doesn't jump away and it doesn't break out and jump away. It is whereas it's similar to its neighbors. Right? Then it is continuous. So we need to use this formula to prove differentiation. Differentiable means continuous. we need to use this formula, which we have. It is differentiable to prove this fact, and to establish this fact that if this is true, is this true? So first, when you do a math problem or proof, you got to figure out, what am I doing here? What is the goal? You have to first figure out what you're trying to prove. So this is what we're trying to prove right here. So we have to go from here to here, and that's what we're going to do. So starting here, we now we're going to pull some trick. A very simple trick is, let's see. We're going to start at this point, okay? In other words, we're going to calculate this thing to see where it goes and see if it gets here. And if it does, then we have proven that differentiation equals implies continuity. So what is the limit? To do the limit as x approach a of f of x, yeah, we're hoping that we'll get to f of a at some point. But right now, it's not that obvious how we're going to get there. But we're going to use this thing because we have it. In proofs, you always use what you are given. What you have, hoping to get to what you don't. Now, so first we start here, and then what? Then we will pull this stunt. What we're going to do is, now this is one of the tricks that you're going to see in calculus proofs. We're going to add and subtract the same thing. So in this case, f of x minus f of a plus f of a. We will minus and subtract. We'll subtract and add the same thing, which means the equation holds. We haven't changed anything. And the first question you might ask is, why are we doing that? We'll see that in a second. But the second question you might think is, where did you get that? How do you even come up with this stuff? The way you do it is you just you sit there, you stare at the wall as a math student, and you throw in random stuff and hope that something works. So, but in this case, the add and subtract is a simple trick that will get things to come out. So, and then the reason we do subtract and add, there's one reason, is because we're trying to make things look like that. So next, we have limit f of x minus f of a. Now we'll take even one more step. We're going to divide it by x minus a. And to do so, you have to multiply by x minus a to be fair. And why we're doing that? This is a blatant attempt to make this thing look like that so we can use it. See? But to divide by x minus a, we have to multiply by the same thing so that we haven't changed anything. And then, yeah. So then this one still stays. This f of a still stays here. So as you can see now, we have made things a lot more complicated. However, that is, but in doing so, we allow ourselves to use this. See? So next step. Next step, we use the rules of the limit that says that when you multiply by stuff, you can take the limit apart, so that it will be the limit of each item. So next, it equals to the limit of the first thing, f of x minus f of a, divided by x minus a. Okay, we're going to break up the limit, and then times the limit of this thing. This is a multiply, times the limit of just x minus a, and then plus the limit of that, f of a. And all these limits are all, what are the limits of? Well, where x is approaching a. X approach a. Now, now this seems like a sort of a fancy and neat trick, but but it isn't done at random exactly, because the goal is to make something look like this, because we have to use this in order to prove our result, because the whole point is differentiable means continuous. If that is true, then we have to use it, the fact that it's differentiable. So this trick enable us to come up with this thing, right? And this thing, as we have been given, is it exists and equals to f prime of a. And that is where we're coming out of the water. Here we're diving deeper and deeper into the water and can barely breathe, but you are coming out. No, right now we're coming out of the water and finally can take a breath. Now this whole thing here is just f prime of a, and then times. Now what happens as x approach the limit as x approach a? Well, that is just 0, okay? Plus the limit of f of a. So this thing gets knocked out by multiplying by 0. Now, isn't that neat? Now, so all we have is limit x approach a of f of a. And that is the proof, because originally that's what we're trying to do. We're trying to prove the limit of f of x as x approach a equals to f of a, which it does. Now, if it equals, then the function is continuous, which therefore we have finished proving that differentiation proves continuity. Now, what about the other way around? If differentiation implies continuity, does continuity necessarily mean the function is differentiable? The answer is no. And the example is on the next page, page 238, where you have this standard example to show how continuity doesn't prove this differentiation. Let's look at the absolute value of x, where you have consider the function f of x equals to the absolute value of x. And from, I don't know, algebra or something, you remember that function has an unusual shape. It looks like this. It goes straight down to 0 and then goes straight up. Well, for a reason. If you think about it, it just takes the positive value of whatever x is, right? So it just does that. Now, at 0, this function is not differentiable. The reason is because differentiation is means that the way that now for this function, if you consider the point at 0 where there is a sharp point, the limit on this side, I mean the slope on this side is -1. The slope on that side is always +1. The slope here, as a result, the limit on the left is always going to be different from the limit on the right of the differentiation. And being that limit only exists if the left limit equals the right limit, then the absolute value of x the function is not differentiable at the origin, being that there's a sharp point. Normally, when there's a sharp point, you can't find the slope. I mean, what's the slope? It's too sharp. I mean, how do you define the slope? There's no way to define it. Even in the microscopic level, even if you zoom in and look at it in a nanometer, it's still sharp. It's sharp no matter how much you zoom in. It's just no way to do the differentiation. There's no slope. So that would be an example of a function that is continuous, but not differentiable at that point. It is differentiable in other spots, though. All this is fine. There's nothing wrong with that. And the next question is, well, you think, well, there's a sharp point there, but there's another example where your function is it has an infinite slope at some point, like this thing. Okay, what is this? This is a cubic root of x. The cubic root of x is continuous and is smooth. It doesn't have any sharp points. But at one point, for a split second, at the origin, the cubic root of x will go straight up for only at the origin, where the which means if something goes straight up, the slope is infinite, approaches infinity, and at that point, then we also say that it's not differentiable because what is the how because the slope is goes to infinity at that point. So that is also called not differentiable but only at that particular point. The rest of it is fine. Now for a third example of something that isn't differentiable. So far we have mentioned that if there's a sharp point, it's not differentiable. If the slope goes to infinity briefly, that's also not differentiable. But there's a third option where stuff is wiggling too much. See this function? It has something to do with x times sine of 1 over x. But it's designed such that the graph just wiggles and then gets smaller and smaller and converges at 0. And then it's not defined as 0, but it goes to 0 though. So that if you define it as 0 for when x is 0, then the whole thing is continuous, surprisingly, because it fits the technical definition of technical requirement of continuity. See, there are technicalities even in math, right? So this thing is continuous, well, strictly speaking, but it is still not differentiable because it's wiggling too much. Okay, so there's a third possibility when a function isn't differentiable is when it's wiggling way too much. Look at this. It's going to move forever, and you can't slow it down to figure out what the slope is at 0. You're barely able to make it continuous, and it's not differentiable. That's asking too much. So those are the three examples where a function might not be continuous. Might not be differentiable, even if they are continuous.